You are currently the only person in this conference.
Welcome back to the virtual classroom of Chembase School of Chemistry. Can you hear me? Sound clear? All can hear me? This discussion is 2021. That's the latest paper, paper 5. I hope all of you have tried the paper. First question, when an alkene is added to a solution of potassium permanganate 7, the purple solution turns colorless. In terms of electron transfer and oxidation number, how does the manganese change in this reaction? Now, manganese is oxidizing agent, and it turns to manganese 2 plus ions. So what happens here is that in terms of oxidation number, that will decrease because manganese is +7, and manganese 2 plus is what is colorless. So oxidation number decreases. Oxidation number will decrease. As for electron transfer, how does the oxidation number decrease? By gaining electrons, right? +7 gains 5 electrons. If you write the half equation, we know it gains 5 electrons and forms the +2. The standard hydrogen electrode uses an electrode of platinum coated in a finely divided form of metal called platinum black. What is the purpose of this coating? Now, the finely divided catalyst, in fact, platinum is acting as a catalyst in this. So that will increase the surface of the catalyst active site. So that results in the equilibrium being established much faster. In other words, the rate of the equilibrium between hydrogen gas and hydrogen ions will be achieved much faster when the catalyst is powdered, because the surface area of the catalyst will increase when it is powdered, right? So the first one looks okay, but we'll analyze the others also, because MCQ questions, sometimes you might see in a question, you will notice 3 correct answers. Sometimes you have questions with 3 correct answers, and you should supposed to mark the correct one. Now, how can there be 3 correct answers, and how can you mark the correct one out of 3 correct answers? Of course, if it's the wrong answer, then it's clear. There can be 3 answers. One is chemistry is correct, but is not relevant to the question. That's not correct. Therefore, even though it's a chemistry is correct, the other 2, the chemistry is correct. Both are relevant, but one explains the question, the situation much better than the other. So you have to analyze all. We can't just rush and we have to read all, right? So the B, provide the inert protective coating for the electrode. No, that's not the reason, because anyway platinum is unreactive. To increase electrical conductivity. No. To ensure that the conditions remains. No. This is the answer. Second one, the answer is A. Electrochemical cell is set up to measure the electrode, standard electrode cell potential, overall cell potential for the reaction given. What is a cell diagram for this cell? Now, cell diagram, always the double line, the parallel 2 lines, the vertical lines, represents a salt bridge. Now, when you draw the cell diagram, or when you write the cell diagram, what you should write on the right side is the reduction. Reduction should be on the right. Easy to remember because right and reduction both starts from letter R, right? So what is reduced here? Tin 2 plus to tin. Decrease in oxidation state is reduction. So tin 2 plus to tin should be your what is written on the right side. So you can see so far 2 answers. So what is written on the left side is the oxidation half equation, iron 2 plus. So we should write as oxidation. And you see now B, we'll only look at B and C because A and D are anyway wrong. So in B, it's written as reduction, right? Fe2 plus to Fe is not oxidation, is reduction. What is written as oxidation is Fe to Fa2 plus. So on the left side, what you write should be written as oxidation, and the right side, what you write should be written as reduction. So 10(2) plus to 10 is reduction. Fe to Fe2 plus is oxidation. This is how you write the cell diagram. Clear? I'm going to just continue one after the other. If you have any questions or if you need any further clarifications, let me know. Standard potential for ion system is minus 0.44 volts, and the E cell for the reaction is plus 0.30 volts. What is the standard electrode potential for tin 2 plus electrode system? So we know E theta cell is E cathode minus E anode. A cathode is the one where reduction occurs. So what is the reduction? Which one undergoes reduction here? The ion, right? Ion, sorry, the tin to tin 2 plus is reduction. So reduction is the cathode. So this is what we need to find. Anode is where the oxidation occurs. Fe to Fe2 plus. Electrode potential is minus 0.44, and E cell is plus 0.30. So what is the E cathode then? 0.3 plus 0.44, get 0.74 plus 0.74 volts, right? Is it correct? No. There's a mistake here. What is the mistake? This is minus, right? Minus is what? Plus. So when you go to the other end, plus becomes minus. So plus 0.30 minus 0.44, right? So 0.3 minus 0.44. So you have to be very careful about that. So you get the answer as minus 0.14 volts. So minus, and this is minus is plus. E cathode minus E anode. Cathode is the one which undergoes reduction. Remember red cat. Remember the term red cat. Reduction occurs at the cathode. That is the right hand electrode, the left hand one. Right hand is where the reduction occurs. Right reduction. Hydrogen oxygen fuel cell can operate in acidic or alkaline conditions. What is the reaction at the anode in alkaline hydrogen oxygen fuel cell? What is the answer? What do you get at the anode? Anode is what terminal in a cell? Anode is the positive or negative terminal. Positive terminal is a cathode in a cell. Anode is a negative terminal in a cell, right? So what happens at the anode? Oxidation occurs at the anode. At the cathode, what happens? Reduction, right? Why we call it as positive negative terminal? Because electrons are released there in a cell, not like electrolysis. Electrolysis cathode is negative, anode is positive. But here the cathode anode is shown by the oxidation reduction. So anode electrons have to be lost. So A is wrong, C is wrong, because electrons are gained. Those are the reduction. So it has to be either B or D, right? So what happens here in a hydrogen oxygen fuel cell? Hydrogen gas reacts with the hydroxide to produce water. It's not hydroxide gives oxygen gas. You don't get oxygen gas in a fuel cell. Hydrogen gas is pumped from one end, oxygen gas pumped from the other end, and series of reactions take place, and the byproduct is water. Here in the B is wrong because oxygen is produced. Oxygen is never produced. Therefore, answer is D. Even see now, even if you don't remember the anode-cathode reaction for oxygen hydrogen fuel cell, you can still work out this way, right? Clear? You notice I pause few seconds after each question. That is for you to ask if you have any questions. I don't want you to ask the question when I start the next one, so we can finish that question and go. So I'll pause about 3 or 4 seconds after each question, so you can ask any questions if you have. Which of these has the greatest number of unpaired electrons in each of its atoms? Greatest number of unpaired electrons. For that, you have to write the electronic configuration. Chromium, if you remember, is 3d5 and 4s1. Iron, if you write the configuration, is what? 3d, 4s2, 3d6. Am I right? Yes. Manganese, 3d5, 4s2. Right? And then vanadium, 3d, 4s2, 3d3. This is the outermost. Right? We had to only consider outermost because the others are all same. Others all same. Right? So which of these has the greatest number of unpaired electrons in each of its atoms? Can you see how number of unpaired electrons here? All the electrons are unpaired. 1, 2, 3, 4, 5. In 3d5, as to the Hund's rule, when electrons occupy, they occupy as singlets before they're doubly occupied. So this has 6 unpaired electrons. But here you have 4s2 pair, and the 6 of the D, 1, 2, 3, 4, 5, 6, 1 is paired. So this can't be the answer compared to chromium. Manganese, likewise, you have 1 pair here and others all unpaired. And 3d3 is only 3 unpaired electrons. So the answer is chromium. Chromium has the highest 6 unpaired electrons in its atomic form, atomic state. 6 unpaired electrons. Nickel is classified as a transition metal. This is because nickel is a D block element. Nay, never. D block elements, not all D block elements are transition elements. What's the definition of transition element? That should be an element which has at least 1 ion with a partially filled d orbital. Form a stable ion with a partially filled d orbital. That is the definition of the transition element. So all transition elements are D block elements, but not all D block elements are transition. In the first 10 series, the scandium and zinc, they are not transition, they are only D block elements. Clear? Platinum forms a complex with the formula. This is diamine dichloroplatinum, and chromium forms a complex with the formula tetrachlorochromate. What are the shapes of these complexes? Shapes of these complexes. We know this cisplatin, transplatin, if you remember, this is square planar. Remember the cisplatin, transplatin, square planar. And this chromium, tetrachlorochromate, if you remember, it is tetrahedral. So square planar and tetrahedral. And of course, we know this is the square planar, right? Because we know the cancer treatment, they use cisplatin, transplatin, remember? Cisplatin is used. So it has to be tetrahedral. So both tetrahedral is wrong. This is square planar. So this is not square planar. The chromium complex is not square planar. It is tetrahedral complex. For that, you have to remember the bond angles. We know the chlorine is a ligand which has 3 lone pairs. It has 3 lone pairs. So they repel maximum. But ammonia is a smaller ligand, not a giant ligand. So when there are giant ligands with many lone pairs, the bond angle will be maximum. So in a square planar shape, the bond angle between each bond is 90 degrees, right? 90 degrees in the square planar. But in tetrahedral, it's 109.5. So when you have bulky ligands like chlorine, it will tend to spread far apart. So therefore, it can't be square planar. Square plane is just 90. It is 109.5 tetrahedral. Right? Clear? What is the bonding between ligands and the central ion in these complex? We know the bonding is dative bond. That's a straightforward question. Coordinate bonds or dative bond. Cobalt chloride is used to test for the presence of water. We know this is a ligand exchange reaction. Cobalt chloride, when the chlorine ligands is replaced by the aqua ligands, the water ligands, the color changes from blue to pink. It's a ligand exchange reaction. That happens, but the reason why the color changes is because the ligands are exchanged. When the ligands exchange, the level of the lower D and the high D orbitals, the DD splitting, the level changes. And then as a result, what happens, the energy absorbed for the DD transition will differ. So the different amount of energy is released. I mean, the complementary color is different. Right, so let's look at the answer for this. This test depends on the fact that the anhydrous cobalt 2 chloride is blue and hydrous cobalt chloride. This is correct, yes. Let's analyze all. Anhydrous cobalt 2 chloride is pink. No, that is wrong. After what is absorbed, it turns pink. Cobalt 2 chloride is blue. Cobalt 3 chloride is pink. No, there's no change in the oxidation state. Water cannot oxidize 2 plus to 3 plus or reduce 3 plus to 2 plus. No, that cannot happen. What happens here is that the ligands are exchanged. It's simply a ligand exchange reaction which takes place. The ligands are changed. What happens? The DD, lower D and the high D energy orbital levels the energy gap will change. So that will result in the different amount of energy absorbed for the DD transition. So the different complementary colors are seen. That's the reason for the difference in color. Iodide ions oxidized by ferroxydisulfate ions. And you know, this is a catalyst. We use a catalyst, Fe2 plus or Fe3 plus also is used. This reaction is catalyzed by adding Fe. Okay, Fe2 plus is the catalyst. So this catalyst is effective because Fe2 plus reacts with the iodide ions and with peron. No, Fe2 plus reacts only with Fe2 plus is reacting with one of the ions, not both. Fe2 means no. This is the answer. Fe2 plus is readily oxidized to Fe3 plus. When Fe2 plus is oxidized to 3 plus, what happens? Iodine get reduced to, thiosulfate get reduced to. This is the reduction oxidation. Thiosulfate is, this is oxidation, right? Let's see, I minus to I2 is increase in oxidation state. This is oxidation. This is reduction. So as Fe2 plus is oxidized to Fe3 plus, that will reduce the persulfate to, this is not thiosulfate, this is a persulfate, also referred to as peroxodisulfate or persulfate. Thiosulfate is S2O32 minus. This is thiosulfate. S4O62 minus is tetrathionate. S2O82 minus is peroxodisulfate or persulfate. You can see if you analyze the oxidation states, the sulfur get decreased. It will decrease the oxidation state of sulfur is reduction, and I minus to I2 is oxidation. So Fe2 plus, as it oxidizes to Fe3 plus, persulfate get reduced to sulfate, and then the Fe3 plus will oxidize iodine to iodine, and itself get reduced to Fe2+. So this is what exactly happens. So you can also use Fe3+ as a catalyst here. In that case, the reverse reaction occurs. I minus and I2 is first, the Fe3+ works on I minus I2, and then Fe2+ works on persulfate and sulfate. So at the end, anyway, the catalyst is reproduced. Catalysts do take part in the reaction, and it is reproduced at the end. The delocalized electrons in benzene result from the overlap of p orbitals to form pi bonds. It's a straightforward question. P orbitals to form pi bonds. The reaction of ethene with bromine occurs under normal laboratory conditions, but the reaction with benzene with bromine to form bromobenzene requires heat and the presence of catalyst. We know is iron 3 bromide catalyst is required. The best explanation for the difference in the reactivity of the delocalized electrons in benzene, we know benzene is a substitution reaction, whereas alkene is an addition reaction, right? Repel electrophiles? No, benzene doesn't repel electrophiles. All reactions of benzene under normal conditions are electrophilic substitution. Results in a kinetic barrier to intermediate formation. Results in a kinetic barrier to intermediate formation. Best explanation for the difference in reactivity of the delocalized electrons in benzene. Yes, because you know benzene, the ring, the delocalized pi ring in benzene is very stable than the delocalized pi electron cloud of alkene. Why is stable? Because the delocalized ring of benzene is formed as a result of combination of many double bonds together. All the double bonds get united and forms a stable ring, right? That means the ring is kinetically stable. This can be the answer. Let's analyze the others. Results in benzene having an endothermic enthalpy of formation. No. Is endothermic enthalpy of formation? It's not the best explanation anyway. Right? Make benzene thermodynamically stable with respect to the formation of bromine. No. Reaction takes place. Reaction takes place. Right? But the difference in the talking about the reactivity, how fast the house or how slow. Right? Difference in reactivity. Benzene is a bit slow, bromination, because of the kinetic stability of the ring. It cannot add, bromine cannot be added to the benzene like you add bromine to alkenes. But you can substitute in the presence of certain conditions like catalysis and heating. Is it clear? What is the name of the compound shown? Let's first number this. 1, 2, 3, 4. This is 2-methyl. 4 carbons but, carbon-carbon single bond N, and this is a functional group which we name it as amide. 2-methyl butanamide. 2-methyl butanamide. Separate 0.1 mole per decimeter cube aqueous solutions of ammonium, butylamine, and phenylamine were prepared. Which of the following sequence shows the solutions in the order of increasing pH? Now, the increasing pH means increasing alkalinity, right? When the alkalinity increases, pH increases. That means you have to be more and more and more alkali. More alkali. Let's see. Butylamine, phenylamine, ammonia. Now, which one is more alkali? Butylamine, right? Because butylamine, the butyl group is electron donating. And then comes ammonia. And then comes phenylamine, because phenylamine, the lone pair of nitrogen is less available. Because lone pair get delocalized with the pi system. So this is the least basic. That means it has the lowest pH. Then ammonia, then the butylamine has a great electron density on nitrogen because of the electron donating C4H7 group. So phenylamine is the lowest pH. Butylamine is the highest pH. Ammonia lies in between. The repeat unit of polymer is shown. What is the structure of the monomer? Now this, as you look at this, you have to identify that this as an addition polymer, because you can see there's no amide or peptide linkage here. So all what you do is you combine and form the monomer. You combine on this pi bond only breaks and forms goes here. This is that pi bond. Goes there, right? Molecules across the pi bond. So the monomer should be this molecule. Let's see where the molecule is shown. Yes, this is the one. The very first one is the answer. Yeah. So whenever you have a carbon-carbon bond as a linkage, then it's addition polymer. Amide or peptide, amide or ester linkage, that's a condensation polymer. Yeah. The repeat unit of the polymer is shown. The polymer could be this. You can see the amide linkage here. That means this has to be one of the monomers, and this is another monomer. Diamine, see, diamine and dicarboxylic. Diamine and dicarboxylic. It's a polyamide. Read the answer. Both polypeptide and polyamide. Polymer could be both polypeptide. No, polypeptide are forms from amino acids. No? Polypeptide, peptide. Polypeptide is for amino acids. Both polypeptide and polyamide. Can't be. There's no amino acids here, right? This is that because amino acid, each monomer has a carboxylic group, amine group. That is amino acid. You have alpha carbon, optically active carbon, where you have amino acids like this. You have a carboxylic group, an H2 group, and an H and R group. So it differs by the R group. So when amino acids forms, we call it as polypeptide. There is no peptide here. So this is wrong. Second, neither polypeptide, no, this is wrong. This is actually polyamide. A polypeptide, but not a polyamide. A polyamide, not a polypeptide. Right? Got it? So polyamide is this amide linkage. Peptide is what we call it only for amino acids. Even the linkage is same, right? Linkage is same. This is a linkage. This is a nylon, like similar to nylon, dicarboxylic diamine. So polypeptide is used for, remember the peptide is used for the amino acids linkages. That is, each monomer has a carboxylic and amine group. Each monomer has a carboxylic and amide group. But the polyamide, one monomer has a carboxylic, both ends carboxylic, and the other polymer, or other monomer has both the ends amine groups. Yeah. Any questions up to this point? Right, the next question. The structure of a hydrocarbon is shown. How many peaks there will be in the C13 Nmr spectrum of this compound? We have to identify the carbons at different environments. Now, these two carbons over here will produce the same peak. They're in the same environment. I'm going to use different colors for different environments. This is one unique environment. And these two carbons will produce the same peak. And then you have these two carbons, same peak, same environment. And then you got this peak, different environment, different carbon, because the neighbors are different. So how many colors I have? 1, 2, 3, 4, 5. So in the C13 NMR, get 5 peaks. Now the C13 NMR, the peaks depends on the number of, the carbons in different environments. If the carbons are in the same environment, that will produce the same peak. Same environment, same peak. Now you see these two CH3 groups. The neighbor of it is a carbon. Same neighbor, right? So it's the same peak. And this carbon neighbor is a CH3 from one end, CH2 from the other end. This carbon CH3 from one end, CH2 from the other end. So this is the same environment. If you take these two carbons, the purple one, the adjacent is a C and a CH2. Adjacent is a C and a CH2. Same environment. If you take these two carbons, adjacent is what? CH2 attached to the carbon. Here, adjacent is a CH2 attached to a carbon, and this end a CH. These are same environment, but this is unique. Attached to CH2, CH2 from both ends. Right? Clear? To get all together 5 peaks. M14, am I clear? When a sample of hydrocarbon is burned completely in oxygen, 2.64 carbon dioxide and 0.81 grams of water is formed. Which of these could be the molecular formula of the hydrocarbon? There are so many ways to do this calculation, but whatever the convenient method can be, shorter method can be used. So we can find the percentage of carbon. Or what you can do is you can write the combustion equation for each and see which one matches the correct masses. Or else you can find the percentages. Right? So complete combustion, 2 carbon dioxide and 3/2 water. So let's this way. How can this be correct? Now what you can do is we can do the other method. Now carbon dioxide, if you take 12 grams of carbon, that will be in 44 grams of carbon dioxide, right? So that means 44 grams of carbon dioxide contains 12 grams of carbon. Got it? Therefore, we can find 2.64 grams of carbon dioxide contains how much of carbon? 12 over 44, 2.64. So 2.64 times 12 divided by 44 is 0.72. grams. Likewise, if you take water, 2 grams, if you take 18 grams of water, there is 2 grams of hydrogen. 18 grams of water contains 2 grams of hydrogen. So 0.81 grams of water contains how many grams of 2 over 18 into 0.81. 0.81 times 2 divided by 18, 0.09 grams. So now what you can do is, you got the masses, carbon is 0.72, hydrogen is 0.09, you find the moles. 0.72 over 12, 0.09 over 1. So 0.72 divided by 12 is 0.06. 0.09. Divide both by the smallest value, 0.06, to get the simplest ratio. I'll just write it here. 1 is to 0.09 divided by 0.06 be 1.1, 1.5. So it's to 2 is to 3. Sorry, 2 is to 3. Is it correct? That is the empirical formula. C2H3 is the empirical formula. But the question answer is not a molecular formula, right? It could be tricky. So easily you can, even I thought the answer is A. But see, it is not A, because it says what? Not empirical. Empirical formula means answer is A. So a molecular formula is a whole number, multiple of empirical formula. Twice of this in this case. Got it? Any questions there? Benzene carboxylic acid may be produced from benzene in 2-step synthesis. This is methylbenzene, and this is the side chain oxidation giving carboxylic acid. 8.24 grams of benzene carboxylic acid was formed in the synthesis. What mass of benzene was used? Let's find. The yield is different, right? 60% and 45%. So you have to go backwards. For that, let's assume 1 mole. 1 mole is 122. So you are using 8.24 moles. Sorry, 8.24 grams. Right? Let's see. So first you find the moles. Moles. 8.24 divided by 122. 8.24 divided by 122. You get the moles as 0.067. That means you need to have 60% of this is what you get here. So moles of benzene, methylbenzene is not this. 60% less of this. That means if you have 100 moles of methylbenzene, you might get only 60 moles. Right? So therefore, if you have 0.0, that means 60 moles, you get, I'll see, if you have 60 moles of 100 moles of methylbenzene, if you have 100 moles of this, you get 60 moles of that. Right? 60 of that. So that's meaning of 60%. Right? So that means 60 to produce, you need to have 100. Got it? 60 moles to produce, you need to have 100 moles of methylbenzene. Therefore, we don't have 60 moles, we have 0.067 moles. 0.067 moles to produce how much of methylbenzene we need? To produce 60, because 60% means 100 gives 60. To produce 60, we need to have 100 of methylbenzene. I'm trying to explain a very simple, basic, explanation. Of course, if you're okay with maths, you can just do it in a very short method, right? So if you have 100, you get 60. That means if to get 60, you need to have 100, right? So therefore, to get this much of moles, you can work backwards. 100 over 60 into 0.67 moles. So that is 67 divided by 60. That means 1.11. Here the answer is 1.116 moles. So here the moles will be 1.116 moles is what we get. So 1.116, 60% is 0.67. And then repeat the same thing again for the other step. Right? We can easily work with the moles. Right? So if you have 100 moles of this, you get 45 moles. That means to produce 45 moles, you need 100 moles. We don't have 45 moles. We got only 1.116 moles now. So 100 over 45 into 1.116 divided by 45, you get 2.48 moles of benzene. Moles of benzene. How to find the mass? You multiply by 78. 193.55. Don't have answer. We had done a mistake somewhere. I think we did a mistake in the calculation somewhere. Can you just check? Is my last 100 divided by 60 into 0.067? I took 0.67. I did a mistake here. 0.0. I thought I didn't put a 0 here, right? See, I did put a 0 here. Right, so it's 100 times 0.067. I forgot the 0. No one corrected me. Divided by 60. 0.1. This is not. This is 0.1116. So 0.1116. So you get the answer as 19.5. 1/10 less. Got it? This is 0.116. 116. So you get 0.116. And this is 0.248 into 78 is 19 point. Here. Any questions there? If you have any questions, let me know. Because most important thing is you understand, not just completing the paper. Even if you just do one question, it's okay. So for you understand it well, right? Because it's not the quantity of work, it's the quality of work. Do one paper properly, that will help you with a proper understanding if you do, rather than doing 100 papers improperly. Right? So if you have any questions, don't hesitate. Clarify before we move on to the next level. Right, no questions? Okay. So we'll take a short brain break before we start the section B. Right, after 5 minutes break, we'll start the next section. Let's continue. I hope everyone is back. The diagram summarizes some reactions of copper compounds. Ammonia, pale blue solid. This is the, we know what is R, right? Copper 2 hydroxide. Let me just write everything here itself, then it's easy. Copper 2 hydroxide. When you heat the black solid, we know only black solid of copper is copper 2 oxide. Copper oxide. And then Ki with copper sulfate, copper iodide with sulfuric. With a pink solid, that has to be copper. Pink solid has to be a copper precipitate. Copper precipitate. Plus the blue solution, copper sulfate aqueous. No, not aqueous copper sulfate, copper 2 plus. And now this is copper sulfate, potassium iodide, copper 1 iodide. Well, sulfuric is a it will convert the copper 1 iodide into copper. Is pink solid is copper. Blue solution, it should contain copper 2 plus ions. So it's hexane for copper 2 plus ions. That's the blue solution. You can just write as aqueous copper 2 plus, or you can write the formula of the whole complex. You can just write Cu2 plus aqueous as well. That has to be the blue solution because copper solutions are blue. Copper solid is pink. And when you add ammonia, you get a colorless solution. V. This is a ligand exchange reaction which takes place. What can this be? Ammonia. Ligand exchange of iodine ligand will be exchanged with the ammonia ligand. Right. Of course, vigorous shaking, dark blue. We know dark blue solution. We know that is tetramine, diaqua copper 2. That is when you add excess ammonia. Ammonia, when you shake it, it reacts further. Tetramine, diaqua copper 2 plus. This complex is the dark blue. Right. So what's this colorless solution here? It has to be a copper plus ion. Copper plus is colorless. So copper plus with ammonia forms a complex. It should be a complex with copper plus 1. Copper plus 1 complex with ammonia. Right, with ammonia. How many ammonia molecules here? Copper plus 1. This should be a plus 1 complex with ammonia. Copper plus 1. Ammonia is maximum 4. This has to be any copper plus 1 complex with ammonia. Just look at the number of moles of ammonia in a while. So this has to be copper plus 1 here because copper plus 1 is a colorless, right? So ammonia will not be 4 here because vigorous shaking will give you more ammonia. So smallest ligand will have, the smallest complex will have 2, minimum 2, right? Minimum 2. Then it can go up to 4 or 6, but copper doesn't form 6 ligands with ammonia because ammonia is a bulky ligand. So it has to be 2. How do you know it's 2? Because vigorous shaking, it gives dark blue solution, and we know that dark blue solution is produced when ammonia, excess ammonia is added to this R. Ammonia, copper 2 hydroxide with the presence of excess ammonia, you get tetramine, copper 2. So we know this T dark blue solution is this. So therefore, the colorless solution, it has to be plus 1 ion of copper because the plus 1 is colorless. 2 plus is blue. It has to be plus 1, and the number of moles of ammonia should be less because you are adding more ammonia here. So minimum number of ligands a complex can have is 2. 2 turning to 4, right? Is that point clear? Even if you know, so the thing is, you might ask me how I know 2. Now, even if you write 2 or 3 or 4, it doesn't matter, right? Doesn't matter because we don't know exactly what is the complex. It is a bit complicated. Now, you can even write this 3 or 4. This is also correct for this because it doesn't matter the number of ligands, but what matters is the charge. Whatever the number of ligands you put, it can be any value between 2 and 4. It can't be more than 4 because this itself is 4. So whatever it is, you have to put the plus sign here. So even this is okay. So what happens in your vigorous shaking? This copper plus reacts with the oxygen and get oxidized to copper 2 plus. This is further oxidation takes place here. So plus turns to 2 plus. So it doesn't matter if you put 2 ammonia, 4 ammonia, 3 ammonia, but not 1. Anything between 2 to 4 is accepted, but not 1. You can't write 1. Right? Clear? So here even copper sulfate is okay. And W, blue solution, copper 2 nitrate. Right? So hold on, this is copper nitrate. Yes. Copper oxide reacting with nitric acid, you get copper 2 nitrate. Copper 2 nitrate plus water. Acid alkali reaction. Acid alkali reaction. Salt plus water. So I have identified all. This is a neutralization reaction. This is oxidation. Clear? T and V are same type of chemical species. T and V. T and V, same type of chemical species. How come that be? T is 2 plus, V is plus 1, but what they mean by same type of chemical species is the ligand is same. Name this type of chemical species. Now, what's the name given for these chemical species? They are complexes, right? This is tetraamine or diamine, copper complex. These are like transition metal complexes. Right? Type of chemical species, transition metal complexes. They are transition metal complexes. Explain why T is colored, why V is colorless. Detailed explanation of the fact that T is colored is not required. Why T is colored and V is colorless. Why T is colored and V is colorless. Why V is colorless? Because V, the copper, is in +1 oxidation state. If you write the electronic configuration of copper, is argon configuration and 3d10 4s1, that is copper. 3d9 never exists. So copper +1 is argon and 3d10. Copper 2 plus is argon and 3d9. So when an orbital is completely filled, like in copper plus, there cannot be dd transitions taking place, right? Because lower d cannot go to the higher d because the orbital is completely filled. But 3d9, there is an empty d orbital. I mean, there is a space for the lower d go to the high level, right? So therefore, at that point, the dd transition can occur in D9, copper 2 plus. Got it? So that's the explanation for that. So in copper 2 plus, you can say the d orbitals are partially filled. So the electrons can transit from the lower d to the higher upper d. Therefore, complementary color can be seen. But in copper +1, d orbitals are completely filled. Copper +1, d orbitals are completely filled. Therefore, electron transitions from the lower d to the upper d cannot take place in copper +1. So we're going to talk about the colored, why it's colored, why it's not. I mean, the reason for the color is not necessary here. Just try to distinguish why one is colored, why is one other one is uncolored. No color. Repeat the answer. Okay, you can say copper +1 ion, d orbital in copper +1 ion, the d orbital is completely filled. Therefore, the dt transition. Therefore, the dd transition cannot take place. Hence, colorless. Whereas in copper 2 plus, there is a partially filled d orbital. Right. Therefore, the d transition can take place. Clear? Right. Next question. Suggest an explanation for the change of V into T on shaking. Already I explained that that is the reaction of the oxidation by oxygen in air. So you can say copper plus 1 is oxidized to copper 2 plus by oxygen in air. Copper plus 1 is oxidized to copper 2 plus by oxygen in air. Shaking, just reacting with oxygen. The reaction between copper and iodide, sulfuric acid is disproportionation. That means disproportionation reaction is a reaction where simultaneous reduction and the oxidation is taking place. You can see here copper 1 iodide, copper 2 plus is reduced to copper 1 iodide. At the same time, copper is also produced. So this is a disproportionation reaction. Copper 2 plus, copper plus 1 turns to copper 2 plus, blue solution. At the same time, you get copper as well. Right? Disproportionation, reaction, simultaneous reduction and oxidation of the same species in the same reaction. Show that the reaction in C1 is thermodynamically feasible. For that, you have to use the standard electrode potential values. You have to get the Cu plus gaining electron, giving Cu copper, and then the next equation Cu plus to Cu 2 plus electron. You have to get the electrode potential values here, and then calculate the E cell value, which is the E cathode minus E anode, and then you construct the overall equation. And you have to prove that overall E cell value is positive. If the overall E cell value is positive, then the reaction is said to be feasible. Right? So if you check the data booklet, copper plus to copper is plus 0.52 volts, and copper plus 2 plus to copper plus is plus 0.15 volts. That is the reduction potential, right? This is reduction, but I have written as oxidation. You can reverse the sign. If you reverse the sign and then try to add, then you should not use the equation E cathode minus E anode. Now this is, I have written as reduction potentials. Electrode potential written as reduction, but I have written the equation as oxidation. So you also have a choice of changing the sign to minus. In that case, you can add simply the two values and get the E cell value. If not, if you substitute the reduction potential, even though you've written this as oxidation potential, then you have to use E cell equals E cathode minus E anode. So cathode is what? Where the reduction occurs, which is 0.52 is a cathode. So 0.52 minus E anode is 0.15. So if you notice, still you get a positive value. So overall cell potential, if it's positive, then such reaction will be feasible. Clear? Don't get confused between the two methods. A rare mineral, meteorite, has a chemical formula given. The mineral, which is 4.2 down. This is a long procedure, right? So when you have a long procedure like this, well, the easiest way to understand is that just you draw a diagram. So you have 4.26 grams of this mineral dissolved in water, and then a beaker in water, and then you translate to see how easy it is when you visualize this in the form of a diagram. 250 ml. By first dissolving in water to ensure that everything dissolves, because you can't put the solid into a volumetric flask and try to dissolve, because some might not get dissolved because you can't put glass rod inside the volumetric flask. You can put the glass rod here and dissolve it. And then you take 25 portion of this. That means 1/10 of what you prepare, and add to that, it says excess potassium iodide is added to this. And what happens here? The Cu2 plus ion reacts with the potassium iodide, and that produces iodine. And the produced iodine is titrated with sodium thiosulfate. Sodium thiosulfate concentration is 0.05 m, right? And the volume in the mean titer is 26.64. That means mean titer is mentioned, means they have repeated this experiment many times and got two concordant results and averaged it, right? For some questions, they don't mention mean titer, they just mention the titer. Then later on in the question, you will notice they will ask you how to improve the experimental procedure. So if the mean titer is not done, just the titer is given, then you can say repeat the experiment till you get concordant results. But in this case, such an improvement is not necessary. The question is, calculate the value of N, number of moles of water of crystallization in this mineral. Now see, let us start from sodium thiosulfate. You find the number of moles of sodium thiosulfate. N equals CV. 1000 contains, what's the concentration? 0.05. And 26.65 contains how much? 1.3325 into the power minus 3. Once you know the number of moles of thiosulfate, you can easily find the number of moles of iodine. That's half of it. And that is the moles of iodine here. And that multiplied by 2 is the moles of copper 2 plus ions. So moles of iodine is half of this. Why half of it? Because 2:1 ratio. And that is moles of iodine in 25, okay? And you can find the moles of copper 2 plus then. Multiply by 2 again. So moles of copper 2 plus in 25. 1.3325, 10 to the power minus 3 divided by 2, multiplied by 2. This answer multiplied by 2. So you get the same answer at the end. Number of moles of copper 2 plus in 25 is same as number of moles of sodium thiosulfate. And then you can find the number of moles of sodium thiosulfate in 250. This is the number of moles in 25. Sorry, the moles of copper 2 plus in 250. 1.3325 10 to the power minus 3 times 10. 1.3325 10 to the power minus 2. Moles of copper 2 plus in 250 was found. Right? Then, what's the next step? You have to now find what? The moles of copper 2 plus is the moles of this, what do you call the mineral? Right? So how to find the mass of the mineral? The moles of copper 2 plus is the moles of the mineral. So that moles multiplied by the molar mass of the mineral. What's the molar mass of the mineral? Moles into molar mass is the mass, right? Can someone tell me the molar mass of the mineral, please? Mineral molar mass without water. That is because water doesn't react with this, with only this part, without water. So let's find 39.1 times 2 plus copper is 3.5 plus 35.5 into 4. That is 283.7. 283.7. So what will that you multiply by 1.3325 10 to the power minus 2. 3.78 grams. That means only the solid is 3. This is 3.78 grams. How much will be the water then? The whole thing is how much? 4.26. So this 4.26 minus this value, 0.47. What is 0.47? Because 0.47 plus 0.3, plus 3.78, you should get the total mass. 4.26. 4.26. Yeah, so 4.26 minus 3.78. 0.48, sorry, this is 0.48. Right? What is 0.48? So you can write, therefore, mass of water 4.67, sorry, 4.26 minus 3.78, 0.48. Right? So you know the mineral and the water. You find the moles. Mineral mass is 3.78 divided by molar mass. We already found the moles here. Water is 0.48 over 18. So here the answer is 1.33 10 to the power minus 2. 1.33 10 to the power minus 2. 0.48 divided by 18 is 0.026. So what's the smallest value? 1.33 10 to the power minus 2, right? So 1 is to this divided by 1.33 10 to the power minus 2. You get the answer as 2. 1 is to 2. So answer is 2. N equals 2. N equals 2. Got it? Any questions there? That's question 19. Ketones are useful starting compounds in organic synthesis. This question is about butanone. The mass spectrum of butanone has a significant peak at mass charge 43 and mass charge 57. The structures of the species responsible for these two peaks. 43, let's break the molecule from here and check whether this is 43. Right, this will be mass charge 43, right? And the 47 You break the whole molecule butanone. What's the molar mass of butanone? That will be 57 plus 15, 72, right? So 72 minus 57 is 15. That means you break a CH3 group. Break a CH3 group. So you can break this corner CH3 group and or other corner CH3, both correct. Any CH3 group you can break. This is mass charge 57. 36 plus 16 plus 5, 57. So you can break this corner CH3 group or the other corner CH3. It doesn't matter. Both correct. The structures of one of the species that you could expect to produce a peak at a different mass charge. Yes, this, if you can break from here, this is 43, other one will be 29. C2H5 group can be formed. C2H5 plus can be formed with a mass of charge 29 easily. Right? Devise a reaction scheme to prepare propane 1-ol from butanone. Now, this is what we call the conversion. Butanone, let me draw the structure of butanone, and propane 1-ol. Propanol. Now see, you should not use more than 4 steps. Each step you should write essential conditions and reagents. Right? Now the thing is, this is a reaction. First, identify what has happened here. 4-carbon compound has turned to a 3-carbon compound. Number of carbon atoms have decreased. Now, to increase the number of carbon atoms is easy, right? We know KCN, HCN, KCN, make sure ethanolic CN. You can use ethanolic KCN to increase the number of carbon atoms. There are only 2 reactions to increase the number of carbon atoms in our syllabus. But how about decreasing number of carbon atoms? There's only one single reaction in our syllabus to decrease the number of carbon atoms. What is that reaction? Yeah, only one reaction is in our syllabus to decrease the number of carbon atoms. What is that reaction? That's right, the iodoform reaction. As you add NaOH, iodine, NaOH, iodine, and warm. You get iodoform, CHI3, triiodomethane, and you get a sodium salt of carboxylic acid, which is, in this case, you get propanoic acid. This part gives the iodoform, the other part gives the sodium salt of the carboxylic acid. Now we have to convert the sodium salt into a carboxylic acid. What we can do is we can add an acid. Any acid we can add. Right? Any acid you can add. Got it? Any dilute acid. Then you can convert this into propanoic acid and reduce the propanoic acid with lithium, aluminium hydride in dry ether condition. You can convert this into the alcohol. Convert that into the alcohol. Reduction. Clear? So I have used only 3 steps. Only 3 steps used. Any questions there? Reduction cannot be done by sodium borohydrate because sodium borohydride is a selective reducing agent, so it has to be only lithium aluminium hydride. The question: is it acceptable if we draw it like this, or must we must explain? You can explain also, but I prefer to draw like this because it's much easier, because we have done so many conversions, right? So it's acceptable to draw. You can easily draw because it's easy to mark, easy to understand, easy to derive. And if you are to write, then of course you might sometimes, there are two options anyway. You can there's drawing, there's space given, and to explain also there is space given. So since there's space given to, first you draw and then you can just briefly explain. You can say, since there's space given for explanation also, you can say carry out iodoform reaction for this, and you get the sodium salt of propanoic acid, and then add an acid to that to convert it into the propanoic acid and reduce the propanoic acid. 3 steps. You can just write briefly. Got it? Okay. Devise a reaction scheme to prepare 2-methyl-butene from butanone. This is butanone. Butanone. See, there are so many conversions. 5 marks given, but you don't usually get more than 4 steps. You get only maximum 4 steps, and you have 2-methyl-butanone. Sorry, 2-methyl-butene. 2-methyl-butene. 2-methyl-butene from butanone. More than 4 steps. Identify the reagents and essential conditions for each step. Right. What can we do? There are so many methods to do this. What do you think? What is the first step? Can we just eliminate? Can we just eliminate HNOH? Methyl-butene. 2-methyl-butene. This is correct. Yes. All that I can think is now it has an extra methyl group, right? That is the issue here. Extra methyl group has come. That means we can add a methyl group by what? We have a Grignard reagent. So a Grignard reagent you can add. Got it? So I have to convert this into alcohol first. Let me just check. Don't copy it. Let me also have to try this and then see if it is correct. And then you convert this into this. But how about the carbon-carbon double bond? No, this is more than 4 steps then. And if you can add a methyl group easily here by a Grignard reagent, but how about the double bond? With a double bond here, right? That is not a good idea. There's a double bond. What do you think? You can put a Grignard and put a CH3 group. That won't be a problem. Right. What can we do here? Now, if you have a difficulty like this, my suggestion should be go reverse, right? I'm just thinking like a student because I can directly write the answer, but I don't want to do that because the reason I have to train you how to think. Now, see, this is 2-meth. We are going to prepare from butanone. So I'm going to draw butanone here. This is butanone. Butanone is butane 2-one, and you have 2-methyl but-2-ene. So now you can go reverse. I can't think forward. It's difficult to think forward. So what you can do is you can go reverse. How to form a carbon-carbon double bond? You can form a carbon-carbon double bond if you eliminate HCl or if you eliminate the HOH, right? That means, look at this. If you have this group, CH3, CH, CN, CH3OH, right? You can eliminate, you can easily form this group, right? You can add HCN, KCN, right? HCN, KCN, you get this. You can put a green out and put a CH3 group, that won't be a problem. Right. What can we do here? Now, if you have a difficulty like this, my suggestion should be go reverse, right? I'm just thinking like a student because I can directly write the answer, but I don't want to do that because the reason I have to train you how to think. Now, see, this is 2-meth. We are going to prepare from butanone. So I'm going to draw butanone here. This is butanone. Butanone is butane 2-one, and you have 2-methyl but-2-ene. So now you can go reverse. I can't think forward. It's difficult to think forward. So what you can do is you can go reverse. How to form a carbon-carbon double bond? You can form a carbon-carbon double bond if you eliminate HCl or if you eliminate the HOH, right? That means, look at this. If you have this group, CH3, CH, CN, CH3OH, right? You can eliminate, you can easily form this group, right? You can add HCN, KCN, right? HCN, KCN, you get this. You get the OH, and you get the CN, and you get the CH3. Then you can easily eliminate the water. You can remove the H and OH, right? Hydration. You had phosphoric acid and hydrated. Phosphoric acid and warm. H and OH will be removed. So CH3, you get CH2 double bond, CN, CH3. Now we have almost come to this closer. So just convert the CN into the CH3. So how can you convert a CN into a CH3? Right? What do you think? So the first step, we can add the Greenard reagent, CH3 MJBr, to get this product. H goes there and the CH3 comes here. And then you convert the OH to PCl5, at PCl5 and convert the OH to Cl. Eliminate H and Cl. What you need to add is CH3, Cl, Mg powder in dry ether. Right, this is the reagent for the Greenard. So it will react to form MgBrCH3. Right? Clear? Let me just check the marking scheme to make sure. Give me a minute. There are so many other options given. You can converting this into directly is also given. They are given marks for that. That means direct elimination is also accepted here, right? Let's just go through the Grignard, and that's because it's a new syllabus. I hope you remember those Grignard reagent, because you will not get any questions in the old. This is the first paper which you have questions on the Grignard reagent. So you have to be familiar with those Grignard questions. So that's very important, because whatever they introduce with the new syllabus, you need to know that, right? So in the magnitude of synthesis, remember, towards the end, I had explained different ways to increase the carbon chain length. So this is tube number study pack 20A. In 20A, if you revise, the first, what I explained, what is Grignard reagent there, and how the Grignard reagent can react in different ways with different compounds. Now, the Grignard reagents, how it is made, you take any haloalkane, bromoalkane or chloroalkane, add magnesium dye to get the RMGPR, that's the Grignard reagent. And so this Grignard reagent, which are nucleophiles, when you react with water, you get the nucleophilic substitution resulting the alkane, and reacting with carbon dioxide, you get carboxylic acid. Reacting with primary alcohols, Grignard reagent with methanol, it will give you a primary alcohol. And this is the reaction, which is Grignard reagent with the secondary ketones to produce secondary alcohol. So what we have produced here is what? What alcohol is this? Right? It is with a ketone, get a tertiary alcohol. This is ketone, right? We react with ketone with a Grignard, we got the tertiary alcohol. So that is, and I have given some conversions here, conversions which involves the Grignard reagent. Right? So to just go through those conversions, and overall, the conversions towards the end of the study pack, which I have given at the end, that is, these conversions are not from the Grignard, other than the Grignard overall organic conversion. So you have to go through all those to revise, in order to revise this. Any questions there? So that's the end of that question. A yellow crystalline solid E dissolved in distilled water to give a yellow solution. Addition of dilute sulfuric acid to this solution produce an orange solution F. Warming F with ethanol results in a green solution G and the formation of ethanol. This is oxidation, right? Orange solution. Yellow solution, we know, we know when you say ethanol is gone to ethanol, that means from this we know that there is oxidizing agent involved, right? This is oxidation. Ethanol is oxidation. So green solution, we know it's Cr3+, and the orange solution should be dichromate, therefore, right? So the yellow crystal solid may be a chromate, because don't know chromium, only complex we know, the yellow complex of chromium is this chromate 6. And that turns to the yellow solution when you dissolve in water. And sulfuric acid, when you add, it's oxidizing agent, so it will add oxygen to this to form dichromate. And dichromate is oxidizing agent. It oxidizes alcohol to partially oxidize to aldehyde because you're not refluxing it, you're just warming it. But if you reflux, it goes to carboxylic acid. So primary alcohol is oxidized to aldehyde, and the oxidizing agent is circuit reduces ER3. So this can be a possible reaction scheme for this. Let's analyze it. The standard cell was set up using solutions F and G. What is F? This is F, green solution, G, F and G. For the right-hand electrode, ethanol, ethanal for the left-hand electrode. So what do you mean by the right-hand electrode? What do you understand? You say right-hand electrode, that means reduction. Reduction has taken place here. Ethanol to ethanal, left-hand electrode, then we know that is oxidation. And overall, E cell is plus 1.94. That means this reaction is feasible. So half equation for ethanol to ethanoic acid is given. So what happens is the opposite, ethanoic to ethanol, ethanol to ethanal. This is ethanal to ethanol. So what actually happens is the opposite. Oxidation of ethanol to ethanal. It is the formula of the ions responsible for the colors of F and G using the standard electrode potentials of E theta given and the values of the data booklet. Right? So what we can do is we can use the E cathode, E anode equation. Right? Of course, I use the inorganic chemistry knowledge here, but it says to use the electrode potential values. So we know E cell, E cathode minus E anode. So E cell value is plus 1.94. And this aldehyde is reduced, alcohol is oxidized to aldehyde, right? So what happens here? Ethanol to ethanal is oxidized, right? Right-hand electrode means is reduction. Reduction occurs at what? Red cathode. So this is what we need to find, and anode is 0.61. Now you can work out the overall cell potential. I mean, cell potential of the cathode reaction. Is this correct? Minus 0.61 anode. Right? So what will be the answer here then? Now this is cathode, right? Cathode equation. Reduction has occurred. Reduction is what? Cr 6 plus to 3 plus. So we'll see that later, right? So what is the answer here? This is cathode or the anode? I think I did a mistake here. Yeah, this is cathode is reduction occurs. So F to G is a right-hand electrode, ethanol to ethanal. This is what we have to use. It's the cathode, right? I did a mistake here. My E cathode is this value. Is minus 0.61 E anode. Right, so what is the answer then? EA is what? Oh, the cathode is, I'm sorry. This is, let me check again. I think I did a mistake. Standard cell was set up using solutions F and G for the right-hand electrode. That is reduction. Ethanol to ethanal for the left hand. This is oxidation. That means this has to be written as oxidation. This is the oxidation. So oxidation half equation, that means this is the anode. This is the anode. So that is correct. What I did before was right. So minus 0.61. Right. So what is the value for this then? E cathode 1.94, 1.33. Okay, 1.33. So 1.33. Let's check with this, right? Plus 0.61. You get 1 point. That's correct. 1.33. So 1.33 is what half equation? Chromate, dichromate to chromium, right? Is that the next question? Yeah, then dichromate to chromium. So dichromate to chromium. You can write the half equation there. Dichromate to chromium. It's 1.33. You can check the data booklet. I earlier did from the inorganic chemistry knowledge, but here it says to use the electrode potential value. So dichromate to chromium is 1.33, orange to yellow, right? You can do that one. So this is the overall equation. So overall equation, which equation has to be reversed? This one has to be reversed, and you should add that to the dichromate chromium half equation. So dichromate to chromium, you add H plus to the side where there's more oxygen, opposite side you add water. These all can be taken from the data booklet also. And you have 6 electrons, and then this is 1.33, and the next one you reverse it. This has to be written as oxidation. So ethanol to ethanol, reverse it. Ethanol to ethanol, and that half equation value you write. And how many electrons are here? There's only 2 electrons, right? 2 electrons and 2 H plus. And you multiply this equation by 3, equalize electrons, and then you add the 2 equations together. Right? You can do that. Write the ionic equation for the reaction of aqueous solution of E with dilute sulfuric acid. What is aqueous solution of E? What is E here? Yellow crystalline solid. E is dissolved in water. So E is what? As I mentioned before, it is the chromate. So chromate with H plus to form dichromate. This half equation, you have to balance it. You put 2 here, and opposite side you add water, and then make it 2H plus. Check whether the electrons are balanced. Yes, it is balanced. Got it? Any questions there? How many more questions to complete? 22. There's section C also. I did went a bit slow today because it's the first paper, right? And I don't want to just rush and give the answers fast, and then no point. It's just a revision lesson as well. So I couldn't complete the paper. Usually I complete one paper in one class. So we're trying to speed up in the next lesson, right? So any questions on what we discussed? I'll complete this paper in the next lesson. And then because I have another class in about 10 minutes, so I cannot continue lessons. But we'll have that extra lesson day. We'll do a little extra. Right, we'll do more. It will take at least 2.5 hours, I think, to complete one paper. So any questions here?